Hi friends, in the last video we have seen how photoelectric effect takes place, right? Now let's just recall the observations quickly. Don't read what is written on the screen, that is just for your future reference. Come back later, pause the video and have a look at it. For now, just listen to what I'm saying. In the last video, we have seen that the photoelectric current is directly proportional to the intensity of the incident light. And we've also seen that the stopping potential is independent of its intensity. And we have also seen that below threshold frequency, no electron emission takes place. And we also saw that the photoelectric emission, that process was spontaneous. Now, if you're not familiar with any of these terms, I suggest you to watch the last video. Let's get started. Einstein said that the photoelectric emission does not take place by continuous absorption of energy from radiation. That is something against the wave nature, right? And he said that the radiation of energy is built up of discrete units. There's a so-called quanta of energy of radiation, and each unit is associated with the energy h into frequency, where h is the Planck's constant, that is equal to 6.626 into 10 power minus 34 joules second. This is a constant. So the energy that each packet has is h into frequency. So in photoelectric effect, the electron absorbs the quantum of energy, this one, and it absorbs this energy, right? And some amount of it is used to break the forces of attraction from the inner ions, that is the work function of the metal, and remaining energy is manifested as the kinetic energy of that electron. So this equation, it looks so simple, right? It is known as Einstein's photoelectric equation, and that is why you saw that if frequency was more, electrons were emitted from some materials. If it is less, what happens? This energy is less, right? And so it was not enough to bring out the electron. Or if frequency is less, this energy associated with one photon, that is one energy packet, will be less than the work function if frequency is less. That is why no electron emission takes place in that case. Each electron doesn't spend that same amount of energy to come out, because some electrons are loosely bound and some are tightly bound, right? So phi naught, the work function, is the amount of energy that you need to give to bring out the most loosely held electron. And that's why when the energy of photon, when you subtract work function from that, what you get is the maximum kinetic energy that electron emitted can have. So the other electrons which spend more energy in coming out will have some less kinetic energy also. Let us try to explain the other observation, that is, when intensity of light falls, when the intensity is increased, the photoelectric current increases, right? Actually, intensity of light is determined by the number of photons that are incident per second. So if more the intensity, what does it mean? It means more number of photons are falling, and it means that more number of electrons are emitted, and that means that more current. That's it, right? And hence, with increase in intensity, you have more current, that is more photoelectric current in the circuit. And however, the maximum kinetic energy depends only on frequency from this equation. That's why Kmax doesn't depend on intensity. Now, photoelectric effect arises from the absorption of single quantum of radiation, right? From absorption of single packet. So whether the electron is emitted or not, it depends on h into frequency. That's it, not on the intensity. And if this will be greater than the work function, then electrons are emitted, right? So how can we calculate the threshold frequency from this? The minimum energy, that is hv0, that is required to bring out a loosely held electron, is that should be equal to the work function, right? So my threshold frequency can be given as work function by Planck's constant. So this is the threshold frequency. Now observe that photoelectric effect is due to absorption of light quantum, that packet, by electron. So this process is instantaneous, whatever may be the intensity. So I can say that whether intensity is low or high, the basic process is same, right? That energy of one packet should be absorbed by electron, and that's why it is instantaneous. The intensity only determines how many electrons are able to participate in that process of ejection. If more is the intensity, more number of electrons take part in the photoelectronic emission, and that's why it is spontaneous also. And in the last video, we've seen that if V naught is the cutoff voltage, then EV naught is the maximum kinetic energy that a electron emitted can have, right? So that Einstein's equation can also be written as in this way: EV naught is equal to h into frequency minus work function. So from this, I can say that my cutoff voltage is nothing but h by E into frequency minus phi naught by E, right? H by E is a constant. Observe that. So I can say that if I plot a graph with the cutoff voltage versus frequency, the slope h by E is going to be constant for all the materials, irrespective of the nature of material. And with this, we are able to explain all the observations which we have seen in photoelectric effect. Photoelectric effect proved that the light in interaction with matter behaved as if it was made of some packets or particles of energy, each with an energy h into frequency, right? So we can see that light behaves as a combination of particles. Here we see the particle nature of light, and each particle or energy packet, that is known as a photon. Again, take a look at these points later. These points just give a rough picture of what particle nature of light. In interaction of radiation with matter, this radiation behaves as if it is made up of some particles called photons, and energy of each photon is given by h into frequency, and momentum is given by h into frequency by c, where c is the speed of light. And note this point: these photons are electrically neutral. That means they are not deflected by electric or magnetic fields, and it's not necessary that number of photons may be conserved in a photon particle collision. Just now we have seen that when a photon falls on an electron, then what happens? Photon is absorbed, right? That is, the photon is lost. It is manifested as energy in the electron later, and this is how you express the energy in terms of lambda, that is the wavelength. It is hc by lambda, and momentum is given by h by lambda. Let us solve this problem. A monochromatic light of frequency 6 into 10 power 14 hertz is produced by a laser. Okay, the power emitted is found to be 2.0 into 10 power minus 3 watt. Okay, what is the energy of photon in the light beam? It is simple. It is given by h into frequency, right? It is 6.626. You can take it as 6.63 into 10 power minus 34, and frequency is 6 into 10 power 14. This comes something like 3.98 into 10 power minus 19 joules. This is energy of one photon. Now the question is, how many photons are emitted per second if this is the power, right? What is power? It is the energy given out per second. So in 1 second, I should get this much amount of energy by these photons. Now each photon can give me this much amount of energy. So if number of photons given out per second is n into this energy 3.98 should be equal to the energy given out in 1 second, right? So this is the equation. Solve for n. You will get n to be 5 into 10 power 15. So these many number of photons are ejected per second. Let us solve another problem. The work function of cesium is given as 2.14 electron volts. I have to find the threshold frequency that will be equal to work function by h, right? We just found out. So this will be 2.14 electron volts by h is nothing but 6.63 into 10 power minus 34 joule second. And note that here it is electron volt. Electron volt is a unit of energy. It is 1 electron volt is equal to the energy which an electron gains after traveling a potential drop of 1 volt. So for converting it into joules, I just have to multiply it with charge of electron, that is 1.9 into 10 power minus 19. So this will be joules again, and here I have the same number, 6.63 into 10 power minus 34. So joule second, and this will give me the answer as 5.16 into 10 power 14 hertz. This is the threshold frequency. Second part of the question is that what is the wavelength of incident light if the photocurrent is brought to zero by stopping potential of 0.60 volts? We just now discussed that the maximum kinetic energy is nothing but charge into the stopping potential, and that is given by h into frequency minus work function, right? So from this equation, I can say that E V naught and frequency can be written as c by lambda, where c is the speed of light, and this will be a new equation. From this I can say that my wavelength is nothing but hc by E into V naught plus work function. This is fine. Just putting the values, h is 6.63 into 10 power minus 34, c is the speed of light 3 into 10 power 8, and here I have, this is what, electronic charge, right? Let it be E only, and V naught is 0.60. It's given that is the stopping potential, and if I put the E as E, this will be electron volts. This is energy, and I know that the work function of cesium is 2.14 electron volts, so I can add them, and finally I'm going to get 2.74 electron volts in the denominator. Just simplifying it, I'll get 19.89 into 10 power minus 26 joule meter in the numerator, and it will be 2.74 electron volts in the denominator. Again, for cancelling I need same units, right? So 19.8 into 10 power minus 26, this should be converted into joules, so I'll multiply it with charge of electron, and that's it. I'm going to get my answer as 454 nanometers. Hope this is fine. In this video we have seen that light, which we know it as a wave, we have seen the particle nature of a wave, right? In the next video we'll see the wave nature of a particle or any matter, say. That's going to be interesting, so keep watching. Bye.